Your app just launched. At first, life is easy. Around 100 users visit your site, pages load instantly, and everything feels smooth. Then one day, your marketing campaign unexpectedly goes viral. Traffic jumps from 100 users to 100,000 users. Suddenly, pages take forever to load, and users begin complaining. Nothing is wrong with your code. The problem is that your existing resources simply can't handle the new workload anymore, and that's exactly why we need scaling. Scaling just means one thing: giving your system the ability to handle more. More users, more traffic, more requests. The first way to scale is called vertical scaling, or scaling up. Instead of adding more servers, we make our existing server bigger by giving it more CPU and memory. Providers like AWS, Azure, and GCP offer predefined machine sizes, and you simply move to a larger one. Vertical scaling is incredibly simple because you have only one server. There's no need to redesign your application for multiple servers. But there's a catch. You're still relying on a single machine. If that server goes down, your entire application goes down with it. The second approach is horizontal scaling, also known as scaling out. Instead of buying a bigger server, you add more servers. Now you might have server A, B, C, D, all working together. But once you have multiple servers, you need a load balancer to distribute traffic across them. Otherwise, users might accidentally pile onto a single server while the others sit idle, completely defeating the purpose of scaling out. This is where things become more interesting. Many applications work perfectly on a single server, but start behaving strangely in a multi-server environment. Take caching as an example. A user lands on server A and adds an item to their cart. The cart data is cached in server A's memory. A few seconds later, the user clicks checkout, but this time, the load balancer sends the request to server B. Server B has never seen that cart before, because the cache only exists in server A's memory. To the user, it looks like their cart randomly disappeared. That's why distributed caching solutions like Redis exist. Instead of storing cache inside a single server, all servers share the same cache. The same challenge appears with session state, such as authentication and user sessions. A user logs in through server 1, but their next request goes to server 3. How does server 3 know the user is already authenticated? In production systems, we usually avoid relying on local session storage and instead use shared session storage or token-based authentication, so every server can validate the user consistently. File uploads create another common problem. A user uploads a file, and server 1 saves it locally. Later, another request is routed to server 2, which has no copy of that file. Suddenly, the file appears to be missing. This is why production systems typically store files in centralized storage services, such as Microsoft Azure Blob Storage or Amazon S3. A useful lesson from all these examples is this: when something is stored inside a server, scaling out often becomes difficult. Storing data in shared services like Redis, databases, and centralized file storage usually makes systems much easier to scale. So whenever you write code, or even when AI writes code for you, and you see data being stored locally on a server, always ask yourself, are we running on one server or multiple servers? Because that one question changes how you handle request data. Since we're talking about multiple servers, let's take a closer look at the load balancer itself. If you're going to explicitly provision and configure a load balancer in a cloud provider, you'll come across several important terms. First, region. Suppose all your application servers are located in the West US region. Where should the load balancer be placed? The answer is simple: in the same region as your servers. If the load balancer is in a different region, every request has to travel across regions, which adds unnecessary latency. It can also increase cost because cloud providers often charge for cross-region traffic. But what if you want a multi-region deployment? In that case, you can use a global load balancer, such as AWS Global Accelerator or Azure Front Door. These services are designed to route users to the closest healthy region around the world. For example, if a user sends a request from India, the system will typically route them to the nearest healthy region, such as an India or nearby Asia region if one is available. This way, users are always directed to the best available region based on latency and availability. Second, public or private. A public load balancer has a public IP address, which means it's exposed to the internet and handles traffic from external users. You would typically use this for public websites or public API. An internal load balancer, on the other hand, uses a private IP address within your virtual network. It isn't exposed to the internet and is used only for traffic between services inside your system. This is common in multi-tier architectures, where you separate your system into web application and backend layers, or when you're building microservices. A simple way to think about it is this. Public means it's reachable from the internet, while internal means it's reachable only within your private network. Third is the health probe. This is how the load balancer determines whether your servers are healthy. It continuously sends health checks to each server at regular intervals, for example, every 5 seconds, to a specific endpoint. If a server repeatedly fails these checks, the load balancer marks it as unhealthy and stops sending traffic to it. Once the server recovers and starts responding successfully again, it is automatically added back into the pool. This is what helps keep your system stable, even when individual servers fail. Now, we can add another layer in front of the load balancer, a CDN, or Content Delivery Network. A CDN is a network of servers distributed around the world that caches static content, such as images, videos, JavaScript files, and CSS files, closer to users. Now imagine your application is deployed in West US, or even across multiple regions using a global load balancer. A user visits your website from India. Without a CDN, even static files still need to travel from one of your application regions all the way to the user. That adds latency and increases load on your servers. With a CDN, those static files can be served from a nearby edge server instead, often located much closer to the user than your application region. In fact, if a request is only for cached static content, it may never even reach your load balancer or application servers. Only dynamic actions, such as logging in, placing orders, or retrieving fresh data from a database, need to travel back to your application servers. This is why CDNs and load balancers are often used together. The load balancer routes users to the appropriate server, while the CDN serves static content from locations even closer to users. Together, they reduce latency, lower server load, and help your system handle massive traffic spikes. Now, here's another problem. Imagine it's 4 a.m., you're asleep, having the best dream of your life. Suddenly, your app goes viral, traffic explodes, your servers are struggling, users are complaining, and now you have to wake up, grab your laptop, and manually add more servers before the system crashes. After this happens a few times, you start thinking, there has to be a better way. And there is. Auto-scaling. Cloud platforms allow you to define rules that automatically add or remove server instances based on metrics. For example, if average CPU usage stays above 70% for a certain period, automatically add another instance. If CPU usage drops below 20%, remove an instance. CPU is just one option. You can also scale based on memory usage, request count, queue length, and many other metrics. However, configuring auto-scaling is not as simple as creating a few rules and walking away. Rules can conflict with each other. Thresholds can be set incorrectly. Cooldown periods can be misconfigured. What's a cooldown period? It's a waiting period after a scaling action. It gives the system time to stabilize and allows the effects of the previous scaling action to become visible before making another decision. Without proper cooldown settings, the system may rapidly scale up and down, creating instability and unnecessary costs. When auto-scaling is configured poorly, you often see frustrating situations like, traffic is spiking, so why aren't new instances being added? Or, traffic is low, so why did the platform suddenly launch so many servers and double my bill? This is why cloud providers publish best practice guidelines for auto-scaling policies. Production systems should follow them carefully and always set up monitoring alerts for scaling events, so you can catch weird behavior early, tune your rules, and improve over time. Now, auto-scaling doesn't always have to react to metrics. Sometimes, traffic patterns are completely predictable, and this is where scheduled scaling helps. Imagine you're building a restaurant ordering system. The restaurant only operates from 7 a.m. till 10 p.m. After 10 p.m., hardly anyone uses the system. In that case, you can schedule the system to scale in automatically at night and scale out again before opening hours. The same idea applies to internal employee systems that are heavily used during business hours, but sit mostly idle overnight. When usage patterns are predictable, scheduled scaling can be simpler, cheaper, and more efficient than relying entirely on reactive metrics. So, scaling is about supporting business growth in the simplest way possible. Start simple. If one server is enough, use one server. When traffic grows, consider scaling up. When a single machine is no longer sufficient, scale out. Use load balancers, distributed storage, CDNs, and auto-scaling only when the business actually needs them. If this video helped make scaling finally click, hit like, share it with a friend, and subscribe for more system design content. Next, I recommend watching this caching video, where we break down the differences between in-memory caching, which works great on a single server, and distributed caching, which becomes essential when you start scaling out across multiple servers.